Here is the dataset that we are going to be using. It's called Airline Delay Analysis, and you can find this on the website kaggle.com. And if I scroll down to the actual dataset, we see that the dataset size is about 8.7 or 9 GB, and we have all these files going back from 2009 all the way to 2019. And you can explore all the data that's already in here on Kaggle. So what I usually like to do is go to the actual dataset source, and that is from the Bureau of Transportation Statistics. And we have all these columns over here and all the data for a range of dates, including for the year 2023 as well. So what I'll do is I'm going to select pre-zipped file and select all these fields and start downloading them one by one, and we will process this data next. Next, what we want to do is upload these files that we've just downloaded into Amazon S3. And a perfect way to achieve that is by using AWS CLI. And if you Google how to install AWS CLI, you will end up on this page where we have instructions for each of the operating system. And in my case, on macOS, I would just have to run these 3 commands. And after running these 3 commands, I can go into my terminal and run AWS version or which AWS, and I should be getting these 2 results. Next, we want to create an S3 bucket where we want to upload these files. So we'll come into the AWS console and come into Amazon S3 page. And when we click on create S3 bucket, we will get a new page like this. And here I'm going to give the bucket name and select the region and a few other things. Block all public access, bucket versioning, I'll disable it. I'll give it a tag and enable encryption and hit create bucket. Once this bucket is created, I can come into my terminal and then say AWS S3 ls. Now this will show me the S3 bucket that I just created. Next is I can list all the files in my directory. And these are all the files that I just downloaded from the website. And I'll be uploading them into my S3 bucket. So with this command, I'm able to recursively load all the files in my directory into my S3 bucket and into a folder called data. Let's also understand why we actually need a graph database and some of its concepts. So there is a concept called 6 degrees of separation, wherein this is you and this is any other person on this planet, maybe the prime minister or president of your country, and you are actually 4 friends away from connecting with this person over here. And these are actually your friends or friends of friends or mutual connections. So this is a statistical concept known as 6 degrees of separation. Now, why is this important? So if we think about in a graph database, we have one person over here and we have another person over here, and they are not directly related, but they are indirectly connected via this person over here. So we are able to find the connections and the relationships between any 2 people because of this graph database. Now, if you think about a social media company or a social platform, you can understand that this can get really complex really, really quickly. And here's another example of why graph databases are necessary. So if you think about a simple table like this, which would be a star schema or a snowflake schema used in a traditional database management system, this can get really complex when you start writing a SQL query like this. This is the length of that SQL query, and an equivalent Cypher query, which is used for querying graph databases, is just 1 line of code like this. Now, there are a few variants here as well. So if I open this up, there is Cypher and also Gremlin query language. It's said that for general querying, Cypher is enough and it's probably faster as well. But if you want to add some complex traversal patterns and your own algorithms, then you can go for Gremlin query language. Let's look at a graph database solution provided by Amazon Web Services, which is called as Amazon Neptune, and it is also available in a serverless service as well. Now, if I click on Launch Amazon Neptune, on this page, we can define all the parameters for creating our cluster. I'm going to select serverless option over here, and this is the version. I will also select this to run in a development mode and give it a name. Capacity, we'll just leave it as it is, and I don't want any multi-regional or multi-zonal cluster deployment at this point. So this we would use if we need high availability between regions, and if there's a failure in one region or a zone, then all the traffic can be redirected to another zone. I'll use the default VPC for now, and the security groups are fine. I'll give it a tag name, and I'll also create a notebook in this instance type, which is 3.3 medium. and I'll give it a name as well and an IAM role, and all these are fine. And finally, I can come in here and click on create database. So some more additional use cases for graph databases are something called as the knowledge graph, where we can ask a question and get answers. Questions like where is this museum located, or where is this place located, or the friends of Lily and when were they born, and etc. So these kind of question and answering, we can use knowledge graphs. There is also something called as identity graphs, where for a single person, we can build out their identity in a graph format where we have customer ID numbers, some device IDs and vendor IDs, maybe usernames, IP addresses, business mail, etc. And then we can build a comprehensive graph of a single person. And of course, there is also social networking graphs where we have friends and then mutual friends, likes, comments, etc. So if you think about leading graph frameworks out in the market, there are two primarily, which is property graph and resource description frameworks, or also RDFs. So with property graphs, a popular framework here is Apache Tinkerpop, which is Gremlin, and this is mostly popular in companies. And the RDF is used in mostly in academics, but it uses a language called as SparkQL. This is Apache Tinkerpop, and you can come in here and read through all these and do a get started tutorial as well. Now, if you think about the architecture of Amazon Neptune itself, so we have Amazon Neptune in the center over here, and we have the ability to use Tinkerpop or RDFs within Amazon Neptune. And we have all these use cases that we can use the graph database for. And on this side, we have, of course, loading data from Amazon S3, database management, and explaining queries, and so many other things that come in here. This is all built upon the AWS infrastructure, where we can go with multi-region availability, read replicas, encryption and rest, and so on. So we have a table like this that we got from either kaggle.com or the original data source from the bureau itself. So how do we go about converting this into a format that our graph database understands? So here is a sample of two different CSV files that we would need to build a graph like this. Now, one of these files should be for all the vertices and the other should be for all the edges. Now, if you remember, vertices are all these green bubbles over here and this yellow bubble, and all the arrows that are connecting these bubbles are called the edges. Right, so edges normally denote all the relationships between the vertices. If you look at this CSV table called vertices really closely, what we have is this notation over here, which is actually used by Gremlin. And in here we have the ID, and we also have the label, and we give a few of these properties for each of these IDs and labels. And the way these vertices are linked with the edges are using these two columns where we have from and to. So if we take the example of one over here, now one is connected to number 3, which is the ID over here, number 3 airport, which is ATL connected to AUS. And the label for this is called the route. So here we would have the label for this arrow is called the route. And the property of this label over here is the distance, which is an integer, and in this case it is 811. So similarly, if we take an example of this and this over here, so we have from 1, and imagine this is 1 in our case, and maybe this is 7 in our case, and there is a link over here, and the distance between them is 546. And even in this case, this vertex over here can have all these properties associated to it. So we have the type, which is an airport, which is also of type string, and the code for this vertex is airport ID, and we have the description, we have the region, we have the runways, and everything associated with this vertex as properties over here. So in our case, we already have the vertices table, which we downloaded, but we have to create the edges table. And one of the primary things that we have here is we need to define the from and to, which is origin and destination. And if we look at the Kaggle site, which provides a preview of our data set, we have the origin and destination. So we should be able to create the edges table based on this initial CSV file that we've been given. Now let's take another simple example and see how all the data is actually stored within Amazon Neptune's graph database. So in this example, again, we have all the vertices over here, and we also have all the edges denoted by these lines over here as well. Now, these vertices are of different types. So we have a user vertices and an account, a group, equipment, and so on. So we have a user who belongs to an account. And how do we define this relationship? That is defined by this belongs to edge. So this is how a graph looks like conceptually. Now let's also look at the raw data that we would need to give to actually build this graph out. So if we were to think about our two CSV files that we need to give, which are in our case the vertices and the edges CSV file. And if you look at this construction contracts vertices, we have all the labels that we saw. We have the user, the account, the group. Of course, we also have the IDs. And within these labels, we have several of the properties, like we saw here, where we have name, email address, and ID. And for equipment, we just have the fuel and maybe the status and the battery. Vertices on their own are not useful because we need to link these vertices together using an edge. So in our case, we also give it the edges CSV file where we define the edge and the from and to, which are the ID. So now we have a good understanding of how the raw input table that we gave looks like and also how the graph looks like. But we still don't understand how Neptune actually stores all this information internally within its graph database. So this is how Amazon Neptune would store all the data that we gave as a CSV internally. And it uses a concept called SPOG, which is subject predicate object graph. So what Neptune would do when it encounters a new entry in the CSV file is it looks at the label. This is called as the user. So it will first come in here, create an entry called label and give it the ID. The subject is P underscore one now. And in this case, the predicate is of the type and it creates a user object over here now. Now, the next thing is to actually define all the properties that we've defined in this object. So it'll come in here and enter all the properties. So in our case for P1, we have name and email, which is Carlos, and the email address. Now, another example is over here where we have the account and Neptune will come in here and add in the subject, which is the IDP underscore 2, and it's of the type account. And it enters all the properties for this, which is just the name over here. So once it does all the vertices, next it encounters the edges file that we would give. So here we have all these edges. Now it does the same thing where it comes in and adds all the edges over here. So it adds the P1 as the subject, and the predicate over here is the actual label, which is belongs to, and the object it is linking to is P2. So in our case, this would be the subject and this would be the object and this would be the predicate, which is what we see here, subject, predicate, and object. So this is how all the information is stored internally within Neptune. And how it helps is when we give it a question like this. So imagine we want to find all the machines, which are all these equipments over here, which can be viewed by Fifth Avenue Construction, which is the group over here. And we have two important information that's already known. So we have the S and the P. The S, the subject, is the Fifth Avenue Construction, and the P predicate is the label, which is can view. And we just need to find the object and the graph. And when we give it this Gremlin code, which is G, which is just the object for the graph, and then we give it the vertex, which is P3 over here. This is our P3 vertex, and we want to find out all the entries that go out and which have a label called can view. And these are all the entries that we have. And when we do get the output, we will get all these equipment as the output. So if you remember, we also created a Neptune cluster. So let's open up the Neptune cluster and the notebook associated with it and run some code. So if I come into Neptune clusters, we can see it's available now. And I'll come into my notebooks and open up my notebooks. So this opens up my notebook, and if I come into the Neptune folder, we see there are already some files already here, and we have a few getting started notebooks as well, which we can run. So here I've got the notebook opened up, and we see there are some notes over here in Markdown and also some code in here. And if I run this cell, we see that it creates a vertex. So all we're doing here is we are using the Gremlin's graph object, and then we are calling a method on it called add or add vertex, and to that we are passing in the label person, and we are also assigning a few properties to that vertex. Namely, we give it a name called Justin. And what we get in return is actually the ID of this vertex. Let me also run a few more cells. So in this case, we are giving a property of ID. And if you notice here, ID is not a within quotes like this because it is reserved keyword and we are giving the ID over here, which also gets returned in the output. Whereas here, when we did the run previously, we got a GUID, which was automatically generated by Neptune. And of course, there are a few more cells here. And there is also add E, which is adding an edge. So here we are adding an edge between vertex number 1 and vertex number 3. And it also has a label called weight of 0.4. Next, we'll do some data pre-processing. But first, let's look at how this data actually looks like by using AWS Glue and Athena. So we already have uploaded these files into our S3 bucket over here. Next, let me open up AWS Glue and set up the crawlers so that we can crawl all these CSV files and start writing some SQL queries against them on Athena. So I'll come in and click on create crawler. So I'll give it airline stats as the name of the crawler, also give it a tag and hit next. Here we'll add the data source, which is the S3 bucket. I'll come into my S3 bucket and copy the S3 URI, paste it in here, and this should be good. We can also create a new IAM role and click next. We can create a database. So now that we have the database created, we can go in here and refresh and select that database. So we can review all the options that we've given, and I'll hit create crawler. So I can select my crawler here and say run. So now the crawler says it is ready and it has succeeded in running. So now we can come into the databases and we see that a database has been created. So if I click into it, we see that we have a table. So I can click into the table and in the actions, I can say view data, which will take us to Athena to preview data. So now when I run this query and look at the results, we have some data that's being displayed over here, and we can see all the columns that this CSV file had. So this data that we have seen within Athena, it's not really compatible to be directly loaded into Neptune. And we also need to create the vertices and the edges file, which is necessary for creating the graph like we've seen in the past. So to create all this, we will use Spark Engine and AWS Glue and use a notebook there to process this data and then create our intermediate files, vertices and edges files. So I can come into AWS Glue and click on notebooks to open up my notebook section. And here we have a way to create the notebook. I already have one running, so I'll just open that up. But if you want to create one, you can just click on this button and choose the engine, which will be Spark Engine, and give it an IAM role as well, and hit on create notebook. Mind you, when you do create this IAM role, we have to give it S3 privileges as well. So here is the role that I'm using, and this has full access to S3. Of course, this is not necessary. This is only for development. When in production, you would only limit this to read access and write access to certain buckets. And I also have a get pass role and Neptune full access as well. This is not completely necessary in our case, but this pass role is necessary. Let me show you what I have here. And within this pass role, I am giving get role and pass role permissions to my service role that I'm using here. And this is necessary when we are running the Glue notebook for it to access S3. So now that we opened our AWS Glue notebook, let's start writing some code. So these are all the initializations, and we will import certain number of libraries that we want to use within our notebook, and also include a few more other libraries which we'll be using for doing some transformations over here and creating the ID. And when we finally run this cell, we will have the Spark session and the Spark context enabled within our notebook. Next, we can also have some arguments, and this is completely not necessary if we are running everything within the notebook. But if you want to run this as an action and run with parameters, so you can give all the parameters here. And one parameter that I wouldn't just show you is just having a job name. And we initialize the job with the job name. And finally, we also get a logger so that we can print logs. Next, I will create my variable with the path to the files that I have stored within S3. And I'll also create one more variable which we will use next, because I don't want to load the entire 365 days or 3 months of data that I've downloaded. I'm just interested in the last 7 days of data. So we'll use this variable to filter out all the other remaining data. Next, I'll also bring in the locations for my vertices and the edges file that I want to save. And I'm just saving it in a folder called notebook for now. And both these files are living in the same directory. So next I can start bringing in my data into this variable called df flight stats raw. For that, I will use my glue context and say I want to create a dynamic frame, and I'll give it a few options where we want to read the file from, and we want to read it from S3, and the path is the path that we've defined here, and the format is the CSV file, and it has a header, and finally we will convert it into a data frame from a dynamic frame. And once I run this, I can also run the print schema, and we can see all the schema of the headers. Next, I can select a few columns within this data frame so that I can double check the values within them. So for here, I will add the flight data column, the origin airport, the origin city, the destination airport, destination city, and finally I will say dot show, which will print out a table like this within the notebook. So if you had noticed what we had in the schema, we have this flight data as a string variable. Now what we want is for this to be an actual date time or a timestamp format. So we will convert this column into that date time format. And to do that, I'm going to take my raw data frame and I'll call with column, and I'm selecting the flight data column, and I will replace this with the function toDate, and I'm giving it the flight column and also the format the date is in, where we can find the format over here. And when I close this off, we will have converted the flight date string into a datetime format, and then that will be stored in df flight stats. So next, what I want to do is get the maximum date that we have within our data frame so that we can filter out and have only the last 7 days of data and discard all the remaining data. So for that, I'll select my data frame that we created over here. I'll run a select on this. And within the select, I will run this max function, and I want to find the maximum date from the flight date column, which we've just converted into a date time format. And within that, I'm just going to get the first value of the array as well, which will give us this output where we see that the maximum date is 31st of March. So next we want to figure out the lower limit of our data frame. So what is the lowest date that we will have within this? And initially we set this variable to last 7 days. So we'll create a time delta out of this. And then I'm calculating the maximum number of days here. And the way I do that is by giving the flight date max, which I got from here, and I will subtract last 7 days from this date. And when I print this out, we will get 24th of March, which is 7 days away from 31st. Next, we'll filter out and get only the last 7 days of data from this stats data frame. So to do that, I will write a where clause, and within here, we will define a filter. So a filter being column flight date greater than equal to the literal values that we found out, which is 24th of March. And I can print this value out and look at the distinct number of flight dates that we have in our data frame. And we do see that we have only days between 24th and 31st of March. Next, we'll start creating the edges file and also the vertices file that can be loaded into Neptune. So to create our edges file, I will select a few important columns such as the origin airport ID, the destination airport ID, and a few other properties here as well. And I can print this out. Now, one of the requirements in our edges file is to have an ID column. So there is no ID column defined in here. So we have to create the ID column ourselves. And we will be using UUID and the UDF function to create our IDs for each of these rows. Next, before pre-processing the entire data frame, we will also add the label and the ID column, which are the required columns for Neptune. So we'll call with column and name our label column over here, and we will just fill this with a literal constant called flight connection for all the rows. And we'll also create the ID column using the function that we've just defined here. So this will go in and create a unique ID for each of the rows in our data frame. Next, we are going to rename a few more header columns so that they are in the format that can be accepted by Neptune. So these from and to are definitely necessary required fields in addition to what we defined over here, which is label and ID. And all the other columns that we are defining over here, these are all the properties that are associated with these airports in our case. So we have the origin code and other code. We are also defining the type over here. And for all the number values, we are defining them as double because we have floating point numbers within our data. Next, we can print a sample of our data frame, and I'm going to select the ID from to label, which are all the required fields for Neptune, and we need to give this special symbol in front of them. And we also print the date as well, and this is the output that we get. Next, we can work on saving this data frame into an actual file. So I'll call first repartition on this file, and we can start saving this using the write mode equals append. And to this, we will give it the format of CSV. I'll also give the option header equals true because we are passing the header in our data frame. And we'll finally save this into our S3 edges location that we defined in a previous cell. And when we run this, this should save the file into our S3 bucket. Next, we will work on creating the vertices file. We'll start with the stats data frame again, and we will select a few of the columns that we are interested in. So if we think about the vertices file, it has all the unique airport and airport IDs. So when we do this, we can select and also run a union and then do a distinct on it to get all the airports within our dataset. So I'll append it to this, the union as well. And within here, we are doing the same. We're selecting all these columns again, but instead of origin airport ID, we are selecting the destination airport ID, and we'll build this out into one big data frame. And we will run a distinct on this so that we only get the distinct values. And if I print only the first row, you can see what kind of values we get here. Next, we also want to add the labels column, which is the required field within the vertices data frame. So to do that, I will add a with column, and here we are calling label and we are adding a literal airport to all the rows. So finally, we can save our file into S3 bucket, and we'll do the same. We'll do a repartition on our vertices file data frame, and we'll save this now by running a write mode append, and we'll give it the format of CSV, and we'll say the header is true, and we'll finally save it into the location that we specified. So this is how you would go about creating the transformation. And finally, you can also get the script as well, which you can run using the run command over here or run with parameters. And when I perform a run over here, we will see that we have run status and everything recorded within the runs tab. Now, if I come into my S3 bucket, I can see that we have two files over here. One is for the vertices and one is for the edges. And if I download and open this, so this is my edges file where we have the from and to. And if I scroll to the right over here, we should also be able to see all the unique IDs. Within our vertices file, we also have the ID column and the label column, which are the required fields. And a few of these are the properties. Now that we have our vertices and edges file within our S3, the next thing is to work on loading this into the Neptune cluster. Before we jump into Neptune cluster, there is one thing that we have to take care of. So if I come into my Neptune clusters, we need to add the IAM roles over here, which we'll be using for loading this data. And there are certain requirements for these IAM roles. So if I come into the documentation, there is a requirement for IAM role here. And we also need to create a VPC endpoint for Neptune to be able to access our S3 files. So if I come into my IAM and roles, I've created a new role called Neptune load from S3. And let me show you the permissions I've given it. So I've given it the S3 read-only access. So in addition to this, we also need to come into trust relationships and copy and paste what we have over here from the documentation. We just copy this and paste it into our section over here. And this role is what we will be using within our cluster. And I can come in here and click on add role and select my role and then press add role. So we already created this notebook in the previous section. So I just open this up. So we'll first import request and JSON, and I'll define my endpoint, giving it the port variable and the server address. And finally, concatenate all this into an endpoint where we have the server and the port. So to get the actual server address, we can come back into Neptune and select clusters. And when I click on this, we will get the endpoints that we can use, or you can come in and directly select the instance and also select this endpoint. So to actually load data from our S3 into Neptune, we will be using the request library and just make a regular post request. And for this post request, I will set my headers content type, and we'll define a data variable where we will also define the source file, which is the notebook folder that I create, which has both the vertices and the edges file. I'll say the format is CSV. I'll also give it the IAM role, which is the Neptune load from S3, which we just created. And to get this ARN, you can come into the IAM role, and for the specific role, you can copy the ARN from here. I'll also specify the region as US East 1. And you can get the region from the cluster details. If I come into my Neptune cluster and if I scroll to the right, you will see that it is in US East 1. I'll also define parallelism to medium and queue request to true and fail on error equals true as well. And next, I'll open up a try except block. And within here, I will make my post request. And within the body of this post request, I will send the endpoint, which is what we've defined here. And I'll also do a JSON dump on this data and also pass in the headers and finally run this cell. So once you run this, you can come in here and look at the status code, which is 200. And you can also print what is actually the JSON response that we get back. In this case, we get a 200 response over here. And we also get a payload with the load ID, which is over here. And we can query this load ID for additional details about how the job went. So for this specific load ID, I can run this GET request on this endpoint and specify the load ID over here. And we'll also add in a few more parameters, such as details equals true, errors equals true, and page equals 1, and error per page equals 3 as well. And when I run this, I will get a response which is a bit more detailed than just getting a response like this. And within here, we can also see if the load was completed. If there are errors, you will get these errors over here. And within this error section, you will start to receive all the logs for the errors here as well, which you can debug. And now that we have our S3 files loaded, we can start querying the data. So I will import a few of the libraries. And first, we will establish a graph traversal object. So first, we'll initialize a graph object. And we'll also establish a remote connection to our cluster over here and give it a cluster URL. And we can initialize the graph traversal and put that in an object variable called G. So we can start running some queries to find all the vertices and the edges that we have just loaded. So I can go run g.v, which is all the vertices, and get a count of that and put that in a list and print all that as well. And get my edges, I will do the same, but instead of v over here, I will specify e for edges and do a count and perform a list operation on that. And when I finally print all the values, we will see that we have 353 vertices and approximately 160,000 edges. Next, we can start writing a few more queries within the graph. And here I will get all the vertices which has a label of airport and do a count on that and also put that into a list. And we will get all the same result as we got over here. And we can do the same on the edges as well. And here I can filter out by label flight connection and do a count on that and also do a list, and we'll get the same value that we got over here. So let me run another query on this. So this time we are looking at the vertices again, and I will get all the vertices with the label airport, and I will do a value map. You will see this in a second, and also limit it to only 5 output. So now if I run this, we get an output like this, and this is where value map is helpful because it just puts everything into one result row like this. And I can do the same on the edges object as well. And we are filtering out all the edges which has the label of flight connection and perform a value map on it and limit as well. And we should be able to see all the properties. Next, I can run a few more queries on the edges as well. So in this case, I will again get all the flight connections. And this time I'm going to group all this by the destination city name column and also order by the local values, and finally do an unfold. And when I run this, in the output, we can see that we have the destination city name and we're doing a group count, which is giving us the count of flight connections. Next, let me run a query on the vertices object. And this time we are getting all the label airport And we have another level of filter over here where we're filtering all the vertices with the origin code equals MCO. And this time I want to find out all the outgoing flight connections from this vertex MCO, and also do a path and give it by origin code. And when we specify path, you can actually see the graph output over here. And when I run this, you will get the output like this. But an even more interesting output is when I come into the graph section and I can visualize the graph that we got here. And of course, in the center, we have the MCO, which is the origin code. And these are all the outgoing flight connections that we have. Next, if I want to find out all the vertices which had the most delay time on it, then I can run this query where I'm filtering out only the airport labels. And here I'm going to find all the outgoing edges and group them by the carrier name. And I'll also do a sum on the departure delay 15 minutes, and I'm calling it a sum function over here. And finally, I will call the unfold, which will give us a result like this. Next, I want to find out all airport connections that had a distance greater than 2000 miles. So for that, I will again tap into the vertex object and filter out only the airport labels. And within here, I'm going to specify that I need all the outgoing edges, which has a distance greater than 3000 miles. And to print out some of these properties, I can also do a value map and say I want the distance, carrier name, and so on. And finally, I will call the path because we want to see this as a graph. And when I run this, you will see that we have all these values, and we also get the distance carrier name, which we specified in our value map. And if I come into my graph, you'll be able to see that we have a graph of all the connections that had greater than 3000 miles distance. And when I'm looking at this, I can click on these vertices and click on this icon, which will give us all the properties listed over here. So these are some basic graph queries that we can run. And of course, there are so many other analysis and ML and analytics. So here within this Jupyter notebook itself, we have a lot of applications such as fraud graph, knowledge graph, identity graph, security graphs, and so on. So that in a nutshell is how we can run an end-to-end pipeline from starting with a data set, loading that into Neptune, and building our graph queries.